welcome to this deep dive. I want to start off by having you ask yourself a pretty mind-bending question right out of the gate.
Oh, starting strong. I like it.
Yeah, well, look at your watch. Or just take a second to feel the present moment passing right now.
Right.
You feel it, don't you? I mean, it feels incredibly real. But what if physics suggests that this feeling, this relentless passing of time, might actually just be a stubborn illusion?
Man, it is one of the absolute most profound questions we can ask.
It really is.
And today, our mission is to unpack time from the absolute smallest atomic level all the way up to the cosmic scale. We are going to figure out if time is just a human construct, maybe a biological quirk or an actual physical fabric of the universe.
Right.
And most importantly, we want to understand what this means for your everyday reality.
Exactly. And to do this, we've got an incredible stack of sources today. We're looking at theoretical physics papers analyzing the highly controversial one-way speed of light.
Which is wild, by the way.
Totally wild. We also have a fascinating MDPI paper exploring the psychobiological reality of how your brain perceives time passage. We're pulling from a deep dive into metrology from the National Institute of Standards and Technology. That's NIST. And we're even bringing in some Reddit ELI5 threads where people break down complex relativity for the rest of us.
Because we definitely need the ELI5 for some of this math.
Oh, absolutely. Okay, let's unpack this.
The best place to start is with the fundamental problem of definition.
Yeah.
Because time is, it's notoriously difficult to pin down. In our NIST source, there is a brilliant quote from St. Augustine that perfectly captures this struggle. Centuries ago, he essentially said, "If no one asks me, I know what time is. If I wish to explain it, I do not know."
That is so relatable.
Right. And even Albert Einstein, after completely revolutionizing our understanding of the universe, ultimately settled on a strictly operational definition. He concluded that time is simply what clocks measure.
Which, honestly, on the surface, that sounds like a bit of a cop-out from one of the greatest minds in history.
It really does.
But it's actually the foundation of modern metrology. Because if time is just what clocks measure, then how we define a second changes the foundation of everything.
Exactly.
It used to be entirely astronomical. A second was just a tiny fraction of the Earth's rotation based on the solar day. But, the Earth wobbles.
It wobbles, it slows down.
Yes, rotation slows down. So relying on the planet wasn't good enough anymore. We had to move to atoms, specifically the cesium-133 atom. Today, 1 second is officially defined as exactly 9,192,631,770 oscillations between the lowest energy states of that specific atom.
You've hit on the exact turning point there. By abandoning the stars and moving to internal atomic frequencies, scientists didn't just redefine time, they literally redefined the entire physical world.
I always think back to the kilogram when this comes up.
Oh, the platinum cylinder.
Yes. Up until 2019, the kilogram was an actual physical object. It was a literal platinum iridium cylinder kept under glass in a vault in Paris.
Le Grand.
Exactly. But the problem with a physical object is that it can lose or gain atoms over time just from microscopic wear or contamination. Someone wipes it down and boom, the official standard for mass for the entire planet has literally changed.
Crazy to think about.
So scientists completely overhauled the system. Now, just like the meter, which is based on the distance light travels in a tiny fraction of a second, the kilogram is derived using foundational constants of the universe, relying heavily on atomic frequencies. Time and frequency have become the ultimate bedrock measurements for our entire understanding of reality.
And our ability to measure those frequencies has reached a level of precision that is, frankly, difficult for the human brain to comprehend.
Yeah, the NIST clocks.
Right. NIST has developed optical atomic clocks that use visible laser light. Instead of oscillating billions of times a second like cesium, this visible laser light ticks 1,000,000 billion times a second.
1,000,000 billion.
Yeah. These clocks are accurate to the 18th decimal place. To put that in perspective, they wouldn't lose or gain a single second, even if you left them running for hundreds of millions of years.
But having a clock that impossibly precise introduces a totally wild problem, which brings us right back to Einstein. Gravity. General relativity tells us that massive objects like the Earth warp the fabric of space-time, and that warping literally slows down time. The closer you are to a massive object, the slower your clock ticks.
Taking that a step further, these optical clocks are so precise they can detect this gravitational time dilation on a human scale.
This part blew my mind.
If you place two of these clocks side by side and lift one just 33 centimeters higher than the other, the higher clock will visibly register time passing faster because it is ever so slightly further away from the Earth's gravitational pull.
33 centimeters, that's like a ruler.
Barely anything.
Yeah.
And they are approaching a precision where they will soon be able to detect a height difference of just 2 centimeters.
That is absolutely wild. It means your head is literally aging faster than your feet.
Technically, yes.
And our NIST source points out a crazy logistical problem this creates. Because the Earth's surface is constantly fluctuating due to tectonic shifts, tides, volcanism, the ground itself is moving up and down by more than a few centimeters. The Earth is literally too squishy for our clocks.
It's too squishy. We might soon have to put our master clocks in deep space just to get away from the Earth's shifting crust and get a stable baseline reading.
It perfectly illustrates how time is not an absolute steady background metronome ticking away uniformly for everyone everywhere.
Not at all.
It is completely relative to where you are and how fast you are moving. Which brings us to the relationship between speed and time.
Yes, let's dive into the Reddit ELI 5 discussion about relativity, because the community there really breaks it down for anyone trying to visualize it without doing the complex math. Imagine you build a spaceship that can travel to the Andromeda Galaxy at 99.99999% the speed of light. From the perspective of your friends watching you through a telescope from Earth, that journey would take about 2.5 million years.
Okay.
But for you, the traveler inside the ship, it would only take 1 minute.
Wait, just to be clear, we aren't talking about a psychological illusion, right?
No, not a trick of the mind. Your biological aging, the beating of your heart, the mechanical ticking of a clock bolted to the wall of your ship, all of it would only experience 1 single minute.
That is so hard to wrap your head around.
It is. To understand why, we have to look at something called length contraction, space and time warp, to ensure that the speed of light remains constant for all observers, no matter how fast they are going.
So the distance actually changes.
Exactly. As your time dilates or slows down, the physical distance you are traveling actually shrinks to compensate. For the traveler in that ship, the actual physical distance to Andromeda literally contracts by a factor of 7,000.
Here's where it gets really interesting. What happens if you actually reach the speed of light? Does the math just completely break?
Well, the mathematics of time dilation are governed by a formula involving the Lorentz factor. As you accelerate closer and closer to the speed of light, the denominator in that equation shrinks, driving the Lorentz factor toward infinity. If an object with mass could reach the speed of light, time would effectively flatline.
Flatline, meaning it stops.
Yes. Let's look at it from the perspective of a photon of light traveling from the sun to your eye. To us, on Earth, we say that journey takes about 8 minutes.
Right.
But from the photon's perspective, 0 time passes. The distance it travels contracts all the way to 0. It experiences its creation at the surface of the sun and its absorption in your retina as a single instantaneous event. It exists in a permanent state of timelessness.
I love the pop culture analogy someone brought up on Reddit for this. They referenced the Pixar movie Lightyear.
Oh, that's a great example.
Yeah, in the movie, Buzz Lightyear takes a test flight to try and reach hyperspeed. To him, he's just up there in the cockpit flying around for 4 minutes.
Yeah.
But when he lands back on his home planet, he finds out that 22 years have passed for everyone else.
Yeah.
Every single time he flies, he stays the exact same age while his friends grow older and older. It's a perfect practical demonstration of how extreme velocity physically detaches you from the timeline of everyone else.
It's a brilliant visualization of relativity and action, but all of this relies on a foundational, unquestioned rule of physics.
The constant.
Exactly, that the speed of light is a universal constant. However, we have a highly provocative paper from ResearchGate in our stack of sources that challenges a massive assumption we've made about this constant.
The 2H trick. This absolutely blew my mind when I read it.
It's a wild concept.
Every measurement we have ever taken of the speed of light, every single one in human history, is actually a two-way measurement. We fire a laser at a mirror, the light bounces back to a sensor, we stop the timer, and we divide the total time by the total distance. We just blindly assume that the trip to the mirror and the trip back from the mirror take the exact same amount of time.
And that assumption is the core of the issue. This paper's thesis is that the one-way speed of light might not be constant in a moving frame of reference at all.
So it changes depending on the direction.
The author argues that light might be anisotropic. That means its speed could vary depending on the direction it is traveling relative to the motion of the solar system.
To explain this, the paper uses a really clever analogy. Imagine you have a train moving at 10 kilometers per hour. Inside the train, there are two horses.
One red, one blue.
Right, one red, one blue. They are running in opposite directions, from the front to the back and the back to the front. Both horses are running at 20 kilometers per hour. To someone standing inside the train, both horses look like they're running at the exact same speed.
Makes sense.
But to someone standing on the ground outside, watching the train go by, the speeds are completely different. The red horse, running in the direction the train is moving, is traveling at 30 kilometers per hour relative to the ground. The blue horse, running toward the back of the train, is only moving at 10 kilometers per hour relative to the ground.
Right.
The paper proposes that our entire solar system is like that train hurtling through the galaxy, and light inside it might be behaving exactly like those horses.
What's fascinating here is that the author actually proposes a physical experiment to test this, rather than just leaving it as a thought experiment.
How do you even test something like that?
They outline a setup involving a massive, incredibly stable spinning disk. You fix a green laser to it, and you meticulously track the drift of highly accurate atomic clocks placed at the edges as the disk rotates. If light travels faster in one direction than the other, the clanks will steadily fall out of sync depending on their orientation to the laser.
And if that one-way variance is proven true, what does that do to physics?
It would be revolutionary. It would mean we could calculate an absolute dead stop in absolute space-time.
A dead stop.
Yeah, a universal background framework that Einstein's relativity explicitly says doesn't exist. It could also explain some incredibly strange anomalies in modern physics, like why we occasionally detect particles called neutrinos that appear to be traveling faster than light.
Oh.
Right. If the one-way speed of light varies, those neutrinos might not be breaking the ultimate cosmic speed limit. They might just be traveling against the motion of our frame of reference, making them appear faster to our sensors.
This raises an important question then. If the speed of light, the ultimate speed limit and measuring stick of the universe varies, depending on the direction we're moving, it means our entire perception of the space and time we are traveling through is completely skewed.
Exactly.
Which forces us to step back and look at the philosophy of reality itself. If our measurement of time is that fragile, if it gets warped by gravity, twisted by speed, and maybe even changes based on direction, what actually is the present?
That is the big question.
Because we all feel like we live in a state of presentism, right?
Yeah.
Only the now exists. The past is just a memory in our heads, and the future hasn't happened yet.
Presentism is our intuitive, everyday reality, but relativity suggests something very different, a concept called the block universe, or eternalism.
Okay, lay this out for us.
Because time is relative to the observer, remember the spaceship to Andromeda, there is no universal cosmic now that slices across the entire universe at the same moment. Therefore, physics suggests that the past, the present, and the future all exist simultaneously in a four-dimensional manifold.
Meaning it's all already there?
Yes. In the block universe, the concept of now is just a coordinate. It's exactly like the word here.
Like a location.
Right. Just because you are standing here doesn't mean the city of London ceases to exist. Similarly, just because you're experiencing now doesn't mean the year 1990 or the year 2050 aren't equally real and out there in space-time.
But if all of time is just mapped out like a giant frozen block, it begs the question, why can't we go back? I know math allows for negative numbers. I've read that Stephen Hawking even used mathematical tricks with time to figure out the Big Bang. But how does that translate to physical reality?
You're referring to a brilliant mathematical trick Hawking used called a Wick rotation.
Right, that's it.
He essentially swapped the concept of time for a spatial dimension. He turned it into something you could mathematically move across just to smooth out the equations of the Big Bang and make the math work. But mathematical possibilities don't always equal physical realities. The equations of general relativity and quantum mechanics are mostly time-symmetric. They work just as well backward as they do forward.
So why are we stuck moving forward?
We're stuck moving in one direction because of the thermodynamic arrow of time.
Okay, so that's the second law of thermodynamics, right?
Right.
Entropy.
Precisely. The second law dictates that in a closed system, entropy, which is a measure of disorder or randomness, always increases over time. The universe began in a state of extremely low entropy, a highly ordered state known as the past hypothesis, and it has been winding down, spreading out, and becoming more disordered ever since. We can't go backward because probability strictly drives the universe from order to disorder.
Wait, let's pause on that. How does the universe getting more disordered explain why I can only remember yesterday, but I can't remember tomorrow? What does entropy have to do with human memory?
It has everything to do with it. Your brain needs to consume energy to form a memory. The act of consuming energy and generating heat increases the overall disorder of the universe.
Wow.
Therefore, the very act of remembering something physically forces the universe forward into a state of higher entropy. You can't remember the future because the physical act of forming a memory is what creates the future. We only remember the past because it was a state of lower entropy.
That completely upends the traditional view of memory. But if time is just a coordinate in a block, and the flow we feel is just a byproduct of entropy and probability, is the passage of time basically just an illusion? I know there are equations in quantum gravity, like the Wheeler-DeWitt equation, where I read the variable for time literally just drops out of the math entirely. The fundamental equations of the cosmos seem to suggest a timeless reality.
That is certainly the perspective of many theoretical physicists. But if we turn to our MDPI paper, which explores the psychobiological illusions of time passage, we get a firm no.
A firm no.
The passage of time is not a mere illusion to be dismissed. It is a very real, measurable psychobiological phenomenon. You see, our brains do not process time as a continuous flowing stream like a video camera recording. Instead, the brain takes discrete, separate sensory inputs and actively stitches them together to construct the feeling of duration and flow.
I read about this in the source. It's like how a movie is just a series of still frames playing really fast, and your brain does the heavy lifting to create the motion. And we know the brain does this because sometimes we can catch it glitching. The paper talks about chronostasis, the stopped clock illusion. I always thought I was just going crazy when I'd stare at the microwave waiting for my coffee to heat up, and that last second seemed to hang there for an absolute eternity.
We've all been there.
But it's a documented phenomenon. When your eyes dart to the clock, they temporarily stop processing visual information, so your vision doesn't blur during the movement. To compensate for that blind spot, your brain essentially backfills that missing fraction of a second with the image of the stationary clock. Your brain is literally rewriting your immediate past.
That is a perfect example of the brain actively generating your reality. The paper also highlights the oddball effect. This is where a totally new sound or image feels like it lasts much longer than a familiar one.
Because it's a surprise.
Well, it feels longer simply because your brain has to expend more neural energy processing the novel stimulus. Our brain is constantly running a predictive generative model, anticipating the future and actively adjusting our sense of now to match the energy it's burning.
Time passage is real because biological systems have to generate it just to survive and navigate the world. But there is a radically new framework emerging in physics that goes even further than biology. It argues that time isn't just a biological construct, and it's not just a background measurement for entropy.
You're talking about assembly theory.
Yes. Proposed by physicists Sarah Walker and Lee Cronin. They argue that time is a physical object. It is the material fabric of the universe itself.
If we connect this to the bigger picture, assembly theory asks us to fundamentally rethink complexity. To build a complex object like a protein, a microchip, or a human being requires a specific history. Simple things like a quark or a single atom don't require memory. With enough energy, they can just pop into existence. But a biological cell requires an evolutionary sequence.
To make sure I'm following, it's the difference between a universe creating a single Lego block versus the universe trying to create a massive 5,000-piece Lego Millennium Falcon.
That's a great way to put it.
A single block requires no instruction manual. But the Millennium Falcon requires history, step-by-step instructions, and a sequential process that cannot be skipped.
That is an excellent analogy. Assembly theory measures this using something called the assembly index, which is the absolute minimum number of steps required to build something. In this view, complexity is quite literally a measure of an object's depth in time. A quark has almost no depth in time. You, as a human being, have billions of years of depth in time.
So time is the instructions.
In assembly theory, time isn't just a ticking clock. It is the physical accumulation of memory and structure. It is the expanding capacity for things to happen.
So what does this all mean? If we put all these massive puzzle pieces together, time is the incredibly precise frequency of an atom that we use to define our modern physical world. It is a dimension that warps and bends around gravity and speed, shrinking distances to absolute zero for a photon.
Beautifully said.
It's a thermodynamic arrow, pointing relentlessly toward disorder, forcing our brains to consume energy just to remember yesterday. It is the biological rhythm of our minds constantly stitching together still frames of reality. And if assembly theory holds up, It is the physical, expanding complexity of the universe itself.
It is all of those things at once, beautifully layered on top of each other. It forces us to reconsider what we mean when we use the word real. A measurement on a clock, a memory in your mind, a thermodynamic gradient, they are all different, highly valid facets of the exact same underlying reality.
So the next time you find yourself glancing at your watch or feeling like a boring meeting is dragging on for an absolute eternity, I want you to remember this deep dive. Remember that your brain is actively generating that exact now by burning neural energy. Remember that your speed through the cosmos and the gravity pulling on your chair are subtly shifting how the watch on your wrist is actually ticking. And remember that your very existence, your biological complexity, is physical, tangible proof of the universe's deep assembly time.
And to leave you with one final provocative thought to mull over. We know that time, as we experience it, emerges from the movement of particles, the increase of entropy, and the building of complexity.
Right.
But what happens trillions of years from now, during the theoretical heat death of the universe? When all the stars have burned out, all matter has decayed into radiation, and the universe reaches a state of maximum entropy where absolutely nothing changes anymore.
The end of everything.
Exactly. If there is no movement, no complexity, and no change, does time itself simply cease to exist?
That is a staggering thought to end on. Thank you for joining us on this deep dive. We hope it gave you a completely new perspective on the ticking clock. Keep questioning the reality around you, keep looking closely at the things you take for granted, and we will see you next time.